Good morning, students.
Good morning, sir.
Good
Good
morning,
morning,
sir.
sir.
Very good
Good
morning.
morning, sir.
Morning, sir.
Morning, sir.
Good morning, sir.
Very good
Good
morning.
morning, sir.
Very good morning. So, in last lecture, what you were discussing? I'm first time sharing my screen. So, in last lecture, what you were discussing? Relativity, Michelson Morley, Lorentz transformation. I think we have completed this derivation. Huh?
Yes, sir.
I think
Yes, sir.
Yes. Yes. So, this is the transformation for T dash. How T and T relation. These are the transformations. And finally, T dash is equal to T minus XV over C square over root 1 minus V square. And students are still coming. Okay. So after that, we have seen that when velocity this V is less than C, then it reduces to the Galilean transformations. Okay. And when V is greater than C, it is imaginary. Okay. Last lecture we have discussed, I think. Right? Okay, so I have given this question. Yes. And students have did this. Any students?
yes, sir.
Yes, sir.
So you can show it to me here and tell me your name. Show it to me and tell me your name. Hmm? Who did this? Can you show it to me? Miss, no one did this, isn't it? So why you not did this? Hmm? What's the problem in this question? I think there is no problem. You are not getting time. Right? You all are very busy. I can understand. Okay. Now my work is to complete the syllabus. Whether you want to do, you can do. If you don't want to do, it's your choice. So today, okay. So now we again come here. Our Lorentz transformation is x dash is equal to x minus vt over root 1 minus v square by c square, and t dash is equal to t minus x over c square over root 1 minus v square by c square. Now what is gamma? This is gamma. I already explained you. What is gamma? Gamma is 1 over root 1 minus v square by c square. Let's say this value v by c is beta. Okay. So for beta is equal to V by C, which is less than 1 for all observer. So if this is less than 1, because C is the maximum speed and velocity of frame can never exceed with this C, so it will be less than 1. Okay. So first condition is that if gamma is greater than 1, gamma is greater than equal to 1. कब होगा?
Velocity 0 होगी.
And velocity is 0, but equal to 1 only when velocity is 0. Okay. Now, if we plot a graph between this factor gamma and V by C means we are increasing the V towards the C. So first value is 0, 0.2, 0.4, 0.7, and we will see this gamma will have the value 1. It is never less than value 1. It will again greater than or equal to 1. And it will increase. And when V is equal to C, what happens? Immediately it goes to the infinity. When V is equal to C, 1 minus 1, 0, root, so it becomes infinity. Okay, so never the velocity of the frame never approaches, never equal to the C. Okay, it's even the imaginary value of space. We give the infinity over here. But at any value very less than C, gamma never go below 1. Okay. So this is a remark we have seen here. If V is very less than C, this is our classical case. Beta almost 0, then we get gamma is equal to 1. So we can see now Lorentz transformation reduced to the Galilean transformation. I have already explained the things. Okay. If V is very less than C, this is our classical case. At that moment, gamma is almost equal to 1 and our Lorentz transformation reduced to the Galilean transformations. Okay, because in Galilean transformations, we have considered the velocity as the classical velocities, not the velocity that is approaching to the velocity of light. Clear? And these are space and time are now not separated. Okay, both are dependent to each other. H dash and T dash is depend on X. Okay, so space and time are now not separated things. So these are our Lorentz transformation. X dash is equal to x minus vt over root 1 minus v square by c square. T dash is equal to t minus vx over c square root 1 minus v square by c. Okay. So for non-imaginary transformation, the frame velocity cannot exceed c. Okay. This already explained the things. We cannot take the velocity that is greater than velocity of light. Property of this gamma. See here, the same thing I have again written over here. Suppose we are taking the velocity v with 1% of c. Okay, this value v taking the value 1% of c. So what is the value we will get? 0.001 c. Substitute over here. Okay, this cancel out. What we will get? See here. If it is very less, 1% of C, even then the gamma is greater than 1. I already told you gamma never go below the 1. 1.0005. Whatever the value, but it have a value greater than 1. Now if take the 10% of C, again we will apply the same thing there. Now it's come 1.005. Okay, so it's increasing now. So this is the complete chart. If frame velocity we increase 0.01, 0.1, 0.5, 0.6 approaching to the C1, V is equal to C over here. So at the moment we will see that here is value 1 point something, always greater than 1, and when it is equal to C, it is infinity. Larger than C, imaginary one. The same graph which I have already explained to you, that graph is represented by this data table. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now what are is the rest frame? K dash is the moving frame. You can take S and S dash frame. Whatever you want, you can take that. That is nomenclature only. Okay. The consequences are, first consequence is simultaneously of event. Simultaneity kya? Two events occur simultaneously in K frame are not necessarily will be simultaneous in K dash frame. Okay. If two events are occur same time in K frame, it doesn't mean necessarily that it will also be at the same time in the K dash frame. I will explain it later. Second, the time dilation. Time dilation means in one frame, suppose there is we put a clock over there and we measure a time interval. So the clock in K dash means moving frame runs slow, means it ticking slow with respect to the clock in S. That is called our time dilation. I will also explain it. And third is length contraction. What is length contraction? Length in K dash frame are contracted relative to the same length in K. Okay. So these are the consequences of the Lorentz transformations. Then again relativistic addition of velocity. Simple addition is not obeyed. Okay. So we will describe all these things, explain with some mathematical mathematical support, how we can show these. Then mass variation. Mass is not constant. I think you know this mass variation. M is equal to m naught over root 1 minus v square by c square. You know this formula?
Yes, sir.
So mass is not equal.
Yes,
M
sir.
is
Yes,
not
sir.
equal to
Yes,
m
sir.
naught. Okay, so mass is not equal. So m not equal to m naught. But there is a factor that is 1 upon root 1 minus v square by c square. So that is called the mass variation. Okay? So these things we will describe here in our special theory of relativity. Invariant, you know, quantity that remains same when transformed from one frame to the another. Okay. See here, what the simultaneity of event. See here, say two events happened at the same time here and different place as measured in A. Let's say this one frame is A frame. Okay. Two events are happened at same time. Time is t equal to tau, time is t equal to tau, but at different place. One event happened at x1 point, other event is happened at x2 point. Clear up to here? Now, do the two events occur at the same time as measured in reference frame A dash? If these two events we are measuring here in S dash frame, in A dash frame, that is moving with velocity v, okay, and that they are occur at the same time measured in reference frame or not. Okay. Now this is our objective. See how we can explain it. Let's say event 1 in this frame A or S, whatever you want to take, x position of x is x1, time let's say t equal to t1 is equal to tau. Second event happened at different place x2, but time same, t is equal to t2 is equal to tau. Clear? Now we apply the Lorentz transformation because now we want to relate these things to the frame A2 or A dash. So we have to use the Lorentz transformation. Okay, when we relate the coordinates from one frame to the another frame, we have the transformations. In classical case, we have the Galilean transformations. But in special theory of relativity, because we are taking the object, those are moving with the velocity of light, approaching to the velocity of light. Here we will take the Lorentz transformations. So now we apply the Lorentz transformation for time. T1 dash gamma, you know gamma is equal to 1 over root 1 minus v square by c square. So we just place only gamma here. Okay. So this T1 minus v over c square x1. Okay. This is the formula. Gamma T1 is tau minus v by c square x1. Similarly, we can find out T2 dash is this one. So the time interval, we are actually measuring the time interval. So time interval is T2 dash minus T1 dash, and this value we will find it is not equal to 0. If time difference will same, okay, then our simultaneity of event is not happen. So the two event does not occur simultaneously in same frame in frame A dash. So this is our simultaneity of event. The two events that happen at the same time in at different place in one frame, so they do not occur simultaneously in frame as test also. So there is a change in the time. Okay, there is a change in the time. So that is called simultaneity of event. Clear? So mathematically we can write t dash is equal to this one and dt dash is equal to dt minus v by c square. And so if the event are simultaneous in frame A, then dt will be 0, giving this. Okay, there will be a change over there. So this is called the simultaneity of events. Means if two events that happened at the same time and different place in one frame, one minute students. उनको बस डाउनलोड कर लो फोल्डर में दे दिया था नहीं वो उसका प्रिंट आउट निकाला था स्टार्ट करें सर आपसे नहीं दैट इज ऑन द फर्स्ट पेज ना हां पूरा उनका हर एक का पूरा निकाल के पूरा निकालना पड़ेगा हां क्योंकि हमको देखना पड़ेगा इसका वो एलिजिबल है नहीं है उसके लिए सब डॉक्यूमेंट देना फिर या तो उसको निकाल के प्रिंट लेंगे उसको बोल दिया था ठीक प्रिंट निकाल के so that we can make that ये भेजना है 3 तक करना है पूरी कंप्लीट पूरा सॉल्यूशन थर्ड तो भी करना पड़ेगा okay so sorry so what I'm saying that if two events happened at the same time and different place will not necessarily not simultaneous in the another frame. Okay, at same time पे वहाँ नहीं होगा because place is different. Now second thing is length contraction. I think I have explained this thing. Length contraction means suppose we have one frame is fixed frame, one frame is moving frame, and we have placed a rod. Okay, in this moving frame. Then observer from here observing this length and observer from over in the same length from here, then there is a change in measurement. There is a change in measurement. So what is this? The length of any object in a moving frame will appear shortened in the direction of motion. In the direction of motion, in this direction only. Okay, where this frame is moving with velocity v. In the direction of motion. Okay, so that means constructed. The amount of contraction can be calculated from Lorentz transformations. The length is maximum in the frame where the object is at rest. So now we will see how we can do this. So I am showing you the derivation. Before the derivation of this, what is proper length? In the last lecture I have explained it. Again I am telling you, to understand length contraction, the idea of proper length must be understood. Let an observer in each system, k dash, whatever you want to take, you can take, have a meter stick in their own system such that each measure same length at rest. Okay. The observer and the meter stick both must be in same frame. Whether frame is moving or rest, for him, meter stick is at rest. ठीक है ना? The observer and the object must be in same frame. Whether that frame is moving or rest. The length so measured is called proper length. Clear? The object and the observer must be in same frame, whether that frame is moving or rest. Okay. Then the length so measured is called the proper length. In this case, we have taken the L node. So here, suppose we have put the rod or meter stick here in S dash frame, and the observer here observing this length. So this will be the proper length or actual length. Okay. And the same rod, the length of the same rod is measured from this frame, observer O, which is at rest. Okay. Then that length is apparent length, not actual length. The apparent length. Okay. So there will be difference between. So L naught in classical mechanics, whether you are measuring this length here in my classroom or when you are measuring in your room, length should be same. Okay. But here in special relativity, the length is changing. Length of the object is changing. But there are certain conditions. Condition is that if frame is moving along x direction, first condition. Second, the objects are moving with very high speed, that is velocity tends to c. Okay, only then this construction can be observed. Clear? So length contraction, this moving body appear to be contracted parallel to their direction of motion. Parallel to their direction of motion. Okay. So now this is my notes. How you can do this? Let's say two frame of reference. Again, we will write the same thing. Two frame of reference, inertial frame, inertial already by default is inertial. S and S dash. S dash is moving with velocity v related to S along positive x direction. Let a rod be placed in S dash parallel to x. If x coordinates of the end, x coordinates, let's say first end is x1 dash, second is x2 dash. Okay. So if x coordinates of the end of the rod, this is nothing. Of rod be x1 dash and x2 dash in S dash frame. Then the length of the rod in S dash frame, what will be the length? X2 dash minus x1 dash. What is the length of this? X2 dash minus x1 dash. So let's say it L0 will be x2 dash minus x1 dash. Let's say this is equation 1. Let observer will be at O in S dash frame. Okay. Now observer is here, second observer, measuring the same length. Okay. So what we will use? Lorentz transformation. So let x1 and x2 be the coordinate along x-axis of the end of the rod at time t. So length of the rod observed by observer from S frame at same time t is L equal to x2 minus x1. Clear? So from this frame, the observer measure x2 dash minus x1 dash, the length of this. From this frame, observer observing the x2 minus x1. Observation of both the end of the rod are taken simultaneously. Events taken simultaneously of event. The same thing. Because measurement has been taken at different place. So according to the Lorentz transformation, x2 coordinates, if I will relate the x2 dash with x2. So relation is x2 dash is equal to x2 minus vt over root 1 minus v square by c square. Okay. Similarly, x1 dash will be x1 minus vt over root 1 minus v square by c square. So L naught will be difference of these two. Take the differences of these two. L naught will be 1 by root 1 minus v square by c square x2 minus x1. What is x2 minus x1? That is L. That is the measurement of the rod or meter stick by the observer O in rest frame. L. L naught is the measurement of the meter stick measured by the observer O dash in moving frame K dash or S dash, whatever you are taking. So see here, L naught is equal to L over root 1 minus v square by c. So this is our surprising result that L naught is not equal to L. In classical case, L naught will be equal to L. But here there is a factor root 1 minus v square by c. So L, so in simplified form, you can write this, take it here, this factor. So you can learn this formula. L is equal to L naught root 1 minus v square by c. So length is changing. Length of a rod of a meter stick in one frame is not equal to the length measured in the another frame that is moving with some velocity. Okay. So there is a change with the factor of this. Clear? Where L naught is called proper length. I already explained this, why this is proper length. Okay, so L naught will be the proper length. The length of a rod placed as just frame appear to be contracted by a factor of root 1 minus v square by c square in the direction of motion to a stationary observer at O in frame. ठीक है? Is there any problem up to here?
No, sir. Yeah.
Okay. Okay, so important point again we will write the case, three case. First case, when V is very less than C. What happened then? V square by C square is very less than 1. So this factor will be almost equal to 1. So L will be equal to L naught. So that case is called, what is that case? Classical case. Okay, that is classical case when velocity is very less than c. Then length will be same, measurement will be same. Clear? Case second, when V is comparable to C, V approaching to C, V almost equal to C, then this root 1 minus V square by C square is very less than 1. Then L will less than L naught. Okay. So this length will be appear contracted. Sort of L is less than L naught. L naught is our proper length.
Proper.
Okay. So measurement from rest frame is length is contracted. In case third, when V is very greater than C. Okay. Then what happen? V square by C square is very greater than 1. This is imaginary, not possible. ठीक है ना? All these three cases we have already explained. So we will write up to here. Then we can say that this derivation is complete. Okay. Now see here, length contraction. This formula L equal to L naught root 1 minus v square by c square. Velocity increasing in this direction. So there is a change. So it become ellipse and all that, and then become ellipse. So this is the picture I have taken from the internet. So you can see. This is the questions which I have given to you. So that x square plus y square plus z square minus c square t square is invariant. So we use the Lorentz transformation substitute here the value, then we get the starting from here, starting from the x dash value, y dash, z dash, c square, t dash. Okay, so x dash is equal to x minus vt over root 1 minus v square, that is beta, gamma, whatever you want to take, right here. So beta square. Y dash is equal to y, remains same. Z dash is equal to z, remains same. C square and t dash is equal to t minus xv over c square into beta. Okay, then we will solve it and put it remains same, y square z square. इसको one side कर दीजिए. Put one side y square z square and solve these two terms. Okay, so solving this, plus y square z square same, plus y square z square same. Solve this, y square z square same. Here. So after solving, these come x square minus c square t square plus y square z square will remain same. Clear? So finally, we arise x square plus y square plus z square minus c square t square. So this is the same quantity, but in rest frame. We have started from the same quantity, but in moving frame, dash, dash, dash. And by applying the Lorentz transformation, we again come to the same quantity. So which show that invariance of this quantity by using the Lorentz transformation. Clear?
Yes, sir.
So this is all about today's lecture.
Yes, sir.
After that, yes. So in the next class, I think we will start with the. I can just give the idea of that. Lorentz time dilation. Clock in S dash frame runs slow with respect to the stationary clock in S frame. Yes. See here. Suppose we placed a clock in S dash frame this, and suppose an event start at some moment. Suppose one person is running. Okay. At time, let's say at that time is t1 dash. When its race is end, at that time is t2 dash. So this time interval t2 dash minus t1 dash measured in this frame, this delta t from this frame are different. Clear? So the objective is we will find this delta t dash in this frame and delta t dash from this frame, and that is we will find here. So difference is delta t is equal to delta t dash upon root 1 minus v square by c square. ठीक है? So this will be the formula.
Sir.
So how I will explain in the next lecture. So this is that.
Okay, sir.
Okay. So time runs slow. When you measure the time from one frame to reference frame, that will be changed. टाइम डायलेशन तो आपने उसमें भी सुना है ना, वो पहले वो होता है ना, क्या बोलते हैं, स्टोरी सुनी होगी आपने अगर हिस्ट्री में, एक राजा थे, आई डोंट नो द नेम ऑफ दैट, और वहाँ किंग ऊपर इंद्र, वो अपना कुछ किसी से उनका वॉर चल रही थी, वो हार गए थे, तो उन्होंने अर्थ से उन राजा को बुलाया. ओके, वो वहां लड़े ऊपर, इंद्र जीत गए इंद्र. Then he told the Indra that now I want to go to earth, okay, to my kingdom. तब इंद्र ने बोला था कि अब आप नहीं जा सकते. अभी क्या है कि यहाँ टाइम 1 or 2 years ही हुए हैं, but in at the earth there are 100 or 1000 years has been passed.
सर एवेंजर्स में हुआ था सर, एवेंजर्स में एंड गेम में सर.
हाँ कहीं है, ये सुना था मैंने कोई. ओके, और
एवेंजर्स एंड गेम.
हाँ कहाँ?
मूवी में सर, एवेंजर एंड गेम.
एवेंजर्स एंड गेम मूवी में
एंड गेम में सर.
आवाज नहीं आ रही. और वो ट्विन पैराडॉक्स
एंटरमेन करता सर क्वांटम फिजिक्स से।
हाँ ये सब सुना है। और ट्विन पैराडॉक्स वाला प्रॉब्लम अगर आपने सुना हो।
सर इट मींस हम सब टाइम ट्रेवल कर रहे हैं क्या?
हम्म।
मींस जब भी हम बुलेट ट्रेन में या फिर किसी हाई स्पीड उसमें जाते हैं तो हम टाइम ट्रेवल कर रहे हैं।
हाँ कह सकते हैं उसको, लेकिन आपको अप्रोच करना पड़ेगा वेलोसिटी ऑफ लाइट। ट्विन पैराडॉक्स इज द सेम प्रॉब्लम, सेम थिंग, मींस टू ट्विन्स। ओके, एक को अर्थ पर रख दिया, एक को स्पेस में छोड़ दिया गया है। आफ्टर 10 years age will be different. Okay, and they have some experimental proof also. Okay, twin paradox problem उसने दिया है ऑर्थर बाइजर, मॉडर्न फिजिक्स, बहुत अच्छे से दिया है। You can read. If the things is interesting to you, then you can read all these things. Okay, so now let's end the class of today, and I will take the attendance. और कुछ काम दिया करें तो उसको करो प्लीज,
Yes, sir.
otherwise there is no
Yes, sir.
totally useless exercise, कोई मतलब नहीं है ना। कोई ऐसा मैं बहुत ज्यादा कुछ आपको असाइनमेंट नहीं दे रहा।
सर इजी वाले सर ने बहुत सारा असाइनमेंट दे दिया था उसमें। इंजीनियरिंग ग्राफिक्स वाले सर ने बहुत सारा असाइनमेंट दिया था सर।
मैं तो कुछ देता ही नहीं हूँ ना। आप एक छोटा सा क्वेश्चन दिया, आप उसको भी नहीं किया। मैं यही बोल रहा हूँ।
अरे सर उसमें बहुत ज्यादा है सर,
हम्म,
इजी वाले चैप्टर में, इजी वाले सब्जेक्ट में।
हाँ ठीक है ना, जब दे रहा आप एक क्वेश्चन आप नहीं कर रहे हैं तो उसका क्या मतलब?
सर नेक्स्ट टाइम से करेंगे सर।
ठीक है ना, नेक्स्ट टाइम देखेंगे। 28 ओके ओके, अटेंडेंस। Okay, I am stopping the presentation. Now I can open this camera now, because if I open this camera, then the disturbing of this internet problem and all that. So I just turn off. Now I can turn off. Okay. Okay, students. Attendance roll number 1.
प्रेजेंट सर।
2,
प्रेजेंट सर।
3,
Present, sir.
4,
प्रेजेंट सर।
5,
प्रेजेंट सर।
6,
Present, sir.
7, 8.
प्रेजेंट सर।
Okay, 9,
प्रेजेंट सर।
10,
Present, sir.
सर 7 प्रेजेंट सर।
7 present. Okay, 11 present. Okay, 12.
प्रेजेंट सर।
Okay, 13. 14.
Present, sir.
15.
Present, sir.
प्रेजेंट सर।